the best English sentence, the best E that satisfies that given this the multiplication of the language model and what we call the language model and the multiplication of the translation model. Okay, so these two things do slightly different things. These two parts of the equation. Okay, the language model is essentially modeling how fluent or grammatical your English sentence is. Okay. And it can be any, you have talked about language models, I assume so. It can be an Engram model, it can be an LSTM, it can be a transformer model, it can be a whatever model you want, as long as it can provide probabilities over English sentences. Okay? And ideally, the best it is. The better it is, the more it will help you. And then you have the second part, which is the translation model, which is the probability of F given E. Remember, what we want to create is E given F, the English given the French. But what we use is the probability in the reverse direction, which essentially measures how faithful is, given that model, the sentence that you have produced. Okay? Because you can produce a very fluent English sentence that has nothing to do with the source that you're trying to translate, right? So that's not what you want to do. So, looking at its components, you can see that there's, we already explained what are the good parts of this model. One measures fluency, the other measures adequacy, how good a translation it is, and both of those models can fail, right? So you might have a sentence that just includes a bunch of really, really rare words, in which case your language model will give it a very low score, right? So you have a sentence like this, that includes words like Churchill, which might have never appeared in any of the other English data that you have ever seen before, or the word spleening, which I assume is a rare word because that's the first time I saw the word ever. I assume it means like something happening to the mother's spleen. That's just an example where if you're trying to translate that, or if that's the best output translation you can get, then there's a chance that your language model score will be low. Now, if we go to the translation model, now this gives the channel probability, the probability for a sentence given another sentence. Okay. So in this example, let's say you have the French sentence, "Je voudrais un pot de fromage," and the correct translation, or one of the correct translations. So that's one more thing to keep in mind, that there's no perfect translation, right? You can have multiple translations that mean the same thing. So, like this example, "I would like some cheese." That's like a proper English sentence that actually translates that French sentence. "I would like a little of cheese." It's kind of sketch, but if I said it as a non-native English speaker, you could understand what I meant, so maybe it would work too. The other sentence, that there's no train to Barcelona, actually is a really, really bad translation. Okay? And the job of the translation system, the translation model, is to assign scores in the opposite direction, right? So given this E, what is the chance that this F was created from this French sentence was created from that English sentence? And, you can also see that, the probability of a possibly slightly less fluent English sentence could be higher. So if you look at a little of cheese, that's the word-for-word translation for un peu de, okay, a little of. So that's why you could, that probability might be slightly higher. So how do you actually parameterize this model? How do you model the translation probabilities for the sentences, right? So one thing you could do is, given your parallel sentences, you can just count how many times a given sentence appears, how many times it appears, how many times an English sentence appears. And then you can count how many times a French sentence appears as a translation of that English sentence, get these counts, and get probabilities over the sentences. Okay? However, there's a ton of sentences, okay? And there's no possible way that you could enumerate all the possible English sentences and all of their possible French translations, right? So a model at the sentence level would be great for anything it has seen before, like if you have you have seen in your training set, but it wouldn't generalize to any new input, right? You might have seen the long cappuccino, short cappuccino, long latte, short latte, but if you have never seen like a long flat white, then you wouldn't be able to assign a score to it. Instead, one solution is to break this down into words. So words are a lot more common, some of them, than complete sentences. So what we do is lexical translations. Okay, so we break up sentences into words, and we translate words. And now the next job, that we also have the problem that we need to scramble to put them back together and to form a fluent sentence. So what did we have in the dictionary? Okay, we have the German word house, which it translates to house or home or household in English, or shell, because within different contexts, house in German, if you're talking about snails, there's very possible that it would mean the shell of the snail. Okay, so even at the word level, we have the issue of polysemy, which means that some words can have multiple senses. Okay, and then you need to rely on other factors in order to properly translate. So keep that in mind also. So, but still, let's say we want to model lexical translation, and we want to get probabilities for house given each of those English words. Then we just look at how common these are, like in our training corpus, right? We have a bunch of parallel English-German data, and we find that, house in English appears 5,000 times, and it has been translated to house in German those 5,000 times. House in German has been translated to home 2,000 times, and so forth. So now you can get probability with a maximum level of estimation, so that the probability of the English translation given the German one, it's just like the number that you had before divided by the sum of the whole column in the previous table, right? So you can have the probability that the translation for the German house should be the English house 70% of the time, 37% of the time it should be home, and 1% of the time it should be shell or household. And now when you have that, again, we have that at the word level, but what we really want is to translate sentences. So putting that back together, if we decompose a vector E or a sentence E into a sequence of words, then we can just get translations for those, making a bunch of assumptions, right? So we have essentially the French, okay, because we want the best English given the French and our model. And now let's say that every English word we generate is because it's generated by one of the French ones. Okay, that makes sense, right? So every English word is translated because it was generated by one of the French words. That means that there's an implicit, like a latent variable that's like an alignment between the French words of the source and the English words of the target. Okay, so we have this alignment, and then essentially, if we have all of these alignments for all of the French words or for all of the English words that are in the target, then the probability of that particular word, if we know where we're generating from, is independent from all the others. Okay, so essentially, this looks like that. On the left side, we have again going from from French to English, given the French sentence, and we also have our model. Now the generative story goes again from left to right. If you look here, given the French, we generate the alignments, and now given the French and the alignments, we generate each of the English words one by one, so that each English word, this EI, at each position, is generated given the French word that it was aligned to. Is that somewhat clear? Or are there any questions at this point? Okay. So essentially, if you think of any generative story that you will ever use where you have anything that's a conditional probability, then you can do. Do you have chocolate?
Why is it chocolate?
Oh. Then anywhere where you have something like P of E given F, right? And you assume that there's a latent variable between. Essentially, you can decompose that to anything that looks like E given whatever that is times right? Or you can do it like that too. And then you can do that as many times as you want. You can have like so that's all we did there. Here we have two latent variables. In this case, we only have one, which is the implicit alignment between the two. Anyway, so a lot of the work in the first 10 years of modern, or like maybe more like 20 years of modern machine translation, which was essentially statistical machine translation, was at figuring this out, right? So words, we have dictionaries, we can get word-for-word translations very well or decently well, but the problem is the word order and how you model that. So alignments, you can think of them as really just links between the source and the target. And then the alignment for this assignment, where it is really the correct one, is also 1 to 1, and it's also monotone. So the alignment at position 1 is source word 1. The alignment at position 2 is source word 2. That's how you would visualize it. But you also might want to include reordering, right? So in Spanish or in Italian, you might put the adjective after the noun, or in French, in some cases. In English, you almost always put the adjectives before the noun. So when you want to say a black cat in English, then in Spanish that might be a gato negro. So the black and cat have been swapped, the words. So you might need to do reordering in order to translate between different languages. So then you might have an alignment like that, where the alignment for source word, for target word 1 in position 1 is source word 3, and so forth. So now we have all of those. One more thing is that you might not want to translate one of the source words, okay? And hence you might drop some of them. Or you might have the opposite, that you might have a word that needs to be there in the target, in the sentence that you generate, that doesn't really align to any of the words. So that's maybe not a very good example, but let's say that the target that you're generating is the house is just small, which is not a very faithful translation of what the German says, because it doesn't really have the just. But, that's just an example, right? In that case, what we did, we assigned a null word, in the beginning of the source sentence, that allowed us to align all the spurious words to that particular null word, and not to any specific word in the source sentence. So one more thing is that this allows for one-to-many translation. So it allows you to translate one source word, like Klitzeklein in German, into two or even more English words, like very small here. But it does not allow you the opposite. So you cannot say that the source for collapsed is actually these two German words, as is the actual correct thing if you know German. So the current model or the models that we have, if we are at the word level, do not allow for something like that. Okay. So going back to the simplest model that you can think of, that was the IBM Model 1, and it was really named IBM because And there's a bunch of other IBM models that were named like that exactly because the people who thought of them and wrote them down in the first day in the was it 87? Well, there's a bunch of similar papers.
Yes.
So either 87 or 90. The people who worked at IBM. It was Brown and someone else. Okay, so they worked at IBM, so these became known as the IBM alignment models. The first one, the most simple, really says that all of the alignment decisions are independent of each other. They have a one-to-one alignment between words. They also allow this null alignment that I talked about. And the original alignment distribution is uniform over all source words and null, which means that, well, we'll talk about that in a minute. So if you have a trained model 1, okay, then for every word in your source, as you generate, you will pick the alignment. So you have you go to the first source, the first position, you choose the alignment for the first position. In this case, it would be the first source position, and you'll generate a sentence, a word. You do that for the second, for the third, and for the fourth, independent of each other. And now you have this candidate translation, and now you can score it with your language model. Remember the other component? So you fill in the slots with the translation model, and you also score it to see if the thing that you output is fluent with the language model. And in this case, the language model might say good translation, give it a high score, or you might have a slightly different alignment, and then given that alignment, you generate a different translation, again, word for word. But in this case, the language model would say, no, that's not a very fluent English sentence. It will give it a lower score. And by doing this over and over, or like over a bunch of hypotheses, then you can pick the one that has the highest combined score, and hopefully you will pick the one that's the best. Okay? So, going back to how can we actually learn the parameters of these models? Have you used EM anywhere in this class? Or
it has been mentioned, but
okay.
In detail.
So, it's really a chicken and egg type of problem, right? If we had perfect alignments, okay, between all of the data that we have in our training corpus, then it would be easy to compute good translations, like lexical translations, okay? Opposite, if we had really good translation probabilities, it would be very easy to produce faithful alignments, okay? So essentially, yeah, so that's what this slide says. So in this case, we use the expectation maximization algorithm, which basically does this process iteratively. So initially, you start with some random or uniform parameters, okay? And then essentially you repeat until bored. And using the current parameters, you generate alignments. And then given these alignments, you re-estimate your parameters. And you do that back and forth a few times. Maybe 4 or 5 times is good enough in our case. And essentially what happens is that, in this IBM Model 1 case, first you start with uniform alignment, right? So any word in any sentence, well, in any word for every pair of parallel sentences, any word here can be aligned to any word here, okay? So you compute essentially not complete count, not integers, but like fractional counts, okay? And now you have all the alignments being equally likely, and maybe the model will learn that la, that appears 3 times, is often aligned with the, if you notice that. So after one iteration, maybe this example will have a slightly higher probability between la and the, rather than say la and house, or la and blue, or la and flower. And then you keep doing that, so now your initial distribution has changed a little, and if you keep doing that, now la and the will become more and more and more likely, and equivalently, others that might be rare will also become more likely, like floor and flower because of the Peter-Hall principle that if the generated la, then something needs to have generated flower, and la doesn't have a lot of probability to give anymore. So basically, essentially, you do another iteration, and in the end, you can take like something like maximum if you want or not, and end up with something that looks very similar to what the correct alignment would be. And now, using your aligner, you can have a proper parameter estimation so that you can know that the probability of la given that should be very high, or la given that, or maison and house is also much higher than, say, maison and flower. Okay. We have, like, you can see some numbers here, for example, where the initial probabilities are all equivalent, like they're all uniform in this very small example, where all of them have the same length, that's why it's 0.25. But then after the first iteration, the things that appear more frequently in the corpus become more likely. And if you keep doing that, then the more frequent stuff will get to go, for example, like that and thus. They will start converging towards 1. Whereas the infrequent stuff, if they are already, they have been assigned somewhere else, they will go towards 0. And then you'll end up with proper alignments after a few iterations. Okay, so going back to the Maori example, actually, so he, you remember the sentences were he, coffee type, maku. Okay, that was the Maori sentence for that was the Maori sentence for I'll have a coffee type. They didn't have a please. Okay, so the actual word-for-word translation for the Maori is he is a or n, so it's the indefinite article. The coffee type is just the coffee type, and maku is for me in the future. Okay, the interesting thing is that again, a lexical model that was just based on a dictionary, that might have translated maku to as for me or something like that, wouldn't have produced an English sentence that would have said, I'll have an espresso, So that's one example where, simple lexical models based on dictionaries might not be good enough. Whereas if we did this process and we learned translation probabilities like you did, so how many iterations did you run? How many iterations of EM did you run when you told me that maku is something? Just easy, okay. But anyway, basically when you looked at all the patterns, you figured out that he, maku as a pattern basically translates to I'll have a something there. Okay? Now, going back to the issue of word-for-word translation and why that's a bad idea is because that rarely is a good thing, right? Maybe the languages are very, 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 very related, so that their vocabulary is very similar, then maybe that's an okay idea. But quite often, what you really translate is phrases to phrases, okay? I don't have it in the slides, but there's the Arquois triangle. Have you guys seen that before? So basically, this looks like, so you have a sentence in English, and then here's the French sentence, okay? So there's an implicit triangle here where, I'm sorry if that's not visible, but essentially here's like the meaning of that sentence, okay? So if we had some way to describe the meaning of that English sentence and the French sentence in a very, like in an interlingua or something like that, or the math logic or with vectors, then you would just need to get English to look like that meaning, and then you would go into French, okay? So some people that you might have seen before, they would say that, going for word-for-word translation is basically like going a little bit here, translating, because you're translating word for word. You kind of capture the word level meaning, and then you're going back. Now, if you're translating phrases, because phrases capture, in a sense, more meaning than single words. Okay, so dio una bofetada in Spanish is three words that give a slap. Okay, but these words by themselves have different meanings than give a slap or slap. You know. So when you're doing phrase-based translation, like what we have been doing, you are closer to that representation of meaning, and then you translate the phrases, and then you can go down to French again. The ideal thing would be to go up to here, okay, and not have to rely on anything like symbolic, but we're not there yet, so there's still lots of work for you guys to do in the coming years. So anyway, so phrase-based NLP essentially apply the very same ideas as for lexical translations, except over phrases. And then it needed a somewhat, not very complicated, but a little complicated, not too, decoding scheme so that you translate all of the source words, and you have all these options for each span. So you can imagine if this is like a graph, that you have probabilities. That Mary did not give a slap to the green witch, right? We have a probability, whereas another path, like Mary did not slap the green witch, has a different probability, which in this case is higher because it's scored higher by either the language model or the translation model or the combination of both. Okay? And that's what we were using for many years. There's also other extensions that you can do to the alignment part. So I don't know if you noticed in many of the examples that we've seen, but the uniform alignment probabilities that we started with in IBM 1 are not really they're not a really good prior, right? In many languages, the general word order might be SVO or SOV, like subject, object, verb, or subject, verb, object, or something like that. The point is that very often translations tend to be fairly monotonic, especially if you're translating between related languages. So imposing such priors that encourage, basically assign higher priors along the diagonal, like this work did with what's called fast align, which is actually out of CMU. You can do a lot better because you start with a better prior, so you have a better alignment, and that leads to better model performance later. Another thing that you can do is to try to also take into account syntax, right? So I'm sure you have talked about syntax and syntax trees and parse trees, but essentially, if you have syntax trees for these two sentences, one in Chinese and one in English. I'm sorry, I cannot read Chinese, but you can see that there's rules that you can apply, which might be more similar to what you did when you were looking at the patterns of the Maori and the English one, right? So this something, how is that symbol pronounced? Does anyone know?
The Australian one?
No, X.
Well, that symbol.
Yeah.
I have no idea.
That translates to one of the. What is it? Okay, I'm not gonna try. But okay, so something and Chuyi. No, maybe. Okay. You can have a rule that says, wherever you see anything like that, translate it to one of the and that. Okay, that X, based on the syntax tree that you have here. So there's all the work, or there was all the work in enhancing NT with these types of rules inferred from syntax. And you could argue that that might put you slightly higher up here, because syntax also helps with encoding with the way that we understand meaning. Okay, so let's say we now have an empty system. So we want to see how well we did. So we'll talk a bit about evaluation. So now, the central idea is that the closer that your output gets to the output that the professional translator would create, then the better the better your system is. Okay, and the most common metric that is used is called blue. Well, blue. I don't know. I pronounce it blue, like the color. So here's how this looks. This basically, you have the candidate on top. That is the output of your NP system. And let's say we got 3 translators to produce translations. Okay. Again, remember, all these 3 translations we deem them to be proper translations because they were created by professionals. Okay. But you can see that they are all different. Okay. So what we do is we find the unigrams that our system produced, and we see if they appear in the references. All right. And you can see that 17 out of the 18 unigrams, words that our system produced, they appear in the references. So our unigram precision is 17 out of 18. Okay. Now you can do the same thing for bigrams, trigrams, 4grams, and even more if you wanted to. Okay. So that's the core idea behind blue. That you do that for unigrams, bigrams, trigrams, and 4grams, and you get an average over them. However, there's issues with n-gram precision. Okay? So let's see an extreme example. Let's say that we have these 2 references. The cat is on the map, and there is a cat on the map. Okay? And our system output the. Alright? And for all of those unigrams, we find the word the in the reference. Okay? So our precision is great, right? We got all of the things that we output are in the reference. All right? So clearly this is not a good metric if we can gain it with something as simple and as clearly bad as this. So the solution to that is a reference word should be exhausted. So you cannot match several candidate words to the same reference word. Okay? So, okay, then instead of producing the, we only produce the once. Okay, I should have changed the references. But let's say now the references are my mom likes the flowers, my mother prefers the blue flowers, okay? And so now we just generated the, right? The appears in the references. So now again we have a precision of 100%, right? Everything we produced appears in the references, so we're good. Clearly we're not good. So now the additional solution to that was to add a brevity penalty that essentially penalizes the system if it produces too short of candidates, given the desired length of the output. So the complete calculation for blue is a geometric average of all the n-gram precisions for unigrams, bigrams, trigrams, and 4grams. But they are clipped, so the precision is calculated so that you exhaust the source, the target word, the reference word when you have matched to it, times a brevity penalty. Okay, and that's actually a score between 0 and 1. If you read MT papers, you'll see that this is typically presented as multiplied by 100, so it's a score between 0 and 100. Depending on statistical significance tests, if you build a system that's one blue point better than another system, then you might have a chance at publishing at a conference paper, or at least at the workshop of WMT or of machine translation. And about a year or 2 ago, the MT system would usually score between 10 and 30 blue points. In the last 1 or 2 years, the MT systems tend to be about 40 to 50 blue points, while professional translators, depending on the language pair, which is important, they might be scoring between 70 and 80, right? So if you evaluate a human translator against another, then your average blue scores will be like 70 or 80 in many cases. It would be way lower for Chinese to English, or English to Chinese, actually. But again, these are like...
because of the language, not because of the translator.
Yes, yeah, because of the language, not because of the translator. Okay, so... Right, so that was up until like 2013 or 2014, okay, where we had these statistical or phrase-based MT systems, and there were a lot of research done on proper alignments in getting better phrase tables, so better translation models, or the next step was better decoding. So how, when you have those models, how do you better combine them in order to produce the final output? Since then, we have basically unilaterally switched to neural models. Although, unless it's Google, Microsoft, or Facebook, most translation models that translation companies might still be using phrase-based models and not neural ones. So, have you talked about neural models here before? Okay.
Some.
Well, okay. So, who has heard of neural models, right? You're seeing you. Okay. All right. So the basic idea is that these are basically this concept that's based on quote-unquote neurons, which are a type of cells that appear in our brain and our neural system. But essentially, some of them, not all of them, perform the following function: they aggregate inputs from other neurons, and by aggregating them, then we might also have like a weight for the aggregation function. So this is what this looks kind of mathematically. And then, given the score of that, they decide to fire or not. And the way that this is modeled is by you have some nonlinear function where if you have a high enough, x times w, then you produce an output. If not, you don't produce an output. Or it's a 0 and 1, or mathematically this can be like between -1 and 1 or something like that. Okay? So when you have that, you can combine many of them and you get what we call a neural network. I'm sure you've seen this before. And again, mathematically, all this is you have a weight matrix, you have your inputs, you multiply them. Right? These are just a vector times a matrix, okay? Or, yes? And then you apply on each output some nonlinear function, okay? And now you can make them deep neural networks, where you just do that twice. So you did that for the first layer, and then you get the output of the first layer. You multiply it with another weight matrix, and then you get that output, you aggregate it, and you put it through a nonlinearity, and that's what you get. Okay? Or you can have, okay, I don't like this figure, but you can have recurrent ones. So when you have multiple things that appear over time, so if you think of a sentence that comes sequentially, okay, from left to right if you're English, or from right to left if you're an Arab, or yeah, that's about it, I guess. Or there's like vertical in some cases, or whatever, right? So there's some order. Then you can have some weights that you apply to the first one. Then you get the second input, and now you apply the same weights in a recurrent manner to the second input. When you get the third one, you apply the same weights, but you keep the previous history in mind. Okay, so don't worry about this figure too much. But there's a bunch of design decisions that go into neural nets, and one of them is how do you represent the inputs and the outputs? Because before we could just collect counts over symbolic units, right? We could see how many times. All we needed was not we didn't care about the representation of the word. We didn't care what characters were there. The only thing we cared was how many times this word appeared. Okay, and if that word appeared enough times, or even just once, then we would have it in our phrase table, and we would know how to translate it. Okay. Whereas with neural models, what you feed in is unclear from that. And then there's other issues like how many layers, how deep do you make your network? How many parameters should you use? Should it be recurrent or should it be not? Or what type of nonlinearity should it be? Should it be a hyperbolic tangent? Should it be something else? So when it comes to representing, like you've talked about embeddings, right? So you've seen probably that where one option would be to just provide one hot vectors. You get all of the English vocabulary, and for every word, you assign an ID to every word, and then in order to feed it as input to a neural net, you're saying, okay, so your input now is this vector, and that essentially means that that's the word go. But of course, maybe that will work for English and its core vocabulary. You cannot, like, it's really not possible to enumerate all of the vocabulary, I think, for any language, right? Even more for languages other than English that are very morphologically rich, and they combine a lot of suffixes or prefixes together in order to make new words in what, that would essentially translate to maybe whole sentences in English. So one solution is to have distributed vectors or embeddings that you have seen before. And hopefully, these could be maybe either handcrafted, so something based on character anagrams or morphological features or anything like that, or they can be not handcrafted and learned through like Word2Vec or whatever you have talked about, or you can just actually learn them while you train your neural net. So how do you train your neural net? Who has trained a neural net? You have trained neural nets. Who has trained neural nets before? Okay. Just to hear you. So basically, for training neural nets, you need supervision. You need to tell them what the desired output is. And the idea is very simple, really. The implementation might be not as simple. Well, these days it's very simple. But the idea is the following. You have your bunch of weights that you have designed, let's say your neural net, like we saw before, okay? And what you need to find is what are the proper values that these weights should have, okay? So the idea is you randomly initialize it, okay? You give it random numbers, okay, for those weights. And now you give it an input and it will produce an output, okay? And that output will be awful, okay? It will be terrible because, it doesn't know anything, it's just random values, okay? However, what you can do now is you know your desired output. So given this difference, you can go and change the weights so that the next time that you see this input, the output is closer to the desired output, okay? And the way that this is done is with, you do a forward pass, which means getting the output, and then you do the back propagation. So you have the desired output, you have your current output, you find their difference, and then you find how you need to change each of those weights in here based on the math and the architecture of your model. And essentially you make those changes. The next time that you see this input, you will be closer to your output. Next time will be closer to the desired output. Okay? I won't go into more detail about that on this, but really that's all it is. Okay? Yeah. So you have talked about n-gram language models before, right? Have you talked about neural language models? No. So with n-gram language models, your job was to, given a context, like 3 words if it's a trigram or 2 words if it's a bigram, to predict the next one. All right? And essentially, you can do that exact same thing with a neural model. You can fit in, if, for example, for a trigram language model, you can fit in the previous 3 words, or their embeddings, and then make a prediction over the output, over the vocabulary about what the next word would be. Okay? So that was the first very simple, feed-forward neural net back in 2013, right? Really all it was you give it the embeddings of the 3 previous words, and it will predict the next word. Okay? And even that, at the time, it did better than n-gram language models with proper smoothing, like the Medernay smoothing, which was the best one. So you can see the perplexity in validation and test. With an n-gram language model, I don't remember what test set I was evaluated on, but basically you can see how the perplexity was like 330 in validation, 320 in test, but the NLP, the neural approaches with different depth, 3, 10, 3, 11, 10, they were all better, so which means that they all had lower perplexity in the last columns. And then essentially you can take that and change it into a translation model. So let's say now we, for some reason, have alignments already based on the previous approaches that we talked, like the IBM alignment model. And now we feed in the 3 French words based on the alignments. or like, we fit in the French word that it was aligned to, and additional context, because why not? And we also maybe have the 3 previous English words that we have generated, right? Even if you have the beginning of the English sentence, that can be just the start of sentence, start of sentence, like you did for English, right? So you can do that, and now suddenly you have a translation model that gives you a translation, like an English word, given not just the previous English words, but also the alignments, the French words that you want to be translating from. And people did that, and it helped again. You can see a bunch of gains over a simple baseline. But again, that was still back in 2014. So let's just simplify the way that this looks. So if you think of the deep nets as if we just show them like that, now the recurrent nets or the LSTMs that you mentioned or other units, essentially they look like that. Okay, you have your input in position 1, you put it through a bunch of parameters, and then you make a prediction. Okay, then you go to the next position, and now you take into account again your input and the previous state or from the previous time step. Okay, and you go like that, and you go left to right or right to left, or in modern architectures you can do both, and you get a bunch of representations of outputs essentially. Okay, so a full neural system basically is 2 of these things combined. The first part encodes the sentence, so it reads the input sentence left to right or right to left or both again. Okay, and it produces a final vector. Right? If you go from left to right, if you think about it, then your final output will have seen all of the sentence. So ideally, it would encode all of the sentence into this one single vector. Okay? And now you can take that vector and, given that, try to generate in the same manner. You generate the first word, and then you fill it in just like a language model. Again, the only difference is that this is a language model with a target language, and it also has received additional input, which was this vector here. But, to quote Ray Mooney, you cannot cram the meaning of a single sentence into just a single vector, okay? Maybe if it's a very short sentence, like I am a student, you can. But if you have a sentence of like length 80 or 100, then you'd need a really, really long, big vector in order to be able to do that for every sentence, okay? So another breakthrough that came just a year later was attention. And now the idea is exactly because the encoder-decoder struggled with long sentences, and essentially one of the reasons was that compressing the meaning of a whole source sentence into a single vector was not optimal. Now instead, what if every time we want to generate a new word on the target side, we look back at the source and we decide where we want to translate. So the idea is like we want to pay attention to a specific part of the source, and given that, receive a vector that we will use to translate. Okay? And hence, this is called the attention mechanism. So that's the intuition, right? So the intuition is that, when you generate the first word, given this source sentence, really, you might not really care what happens at the end, but if you know that, the context that you need to be paying attention to are these 2 first words, then you can pay attention to that and then generate the output. And you can keep going like that. Okay? Now, this looks a lot like alignment, like we saw before, right? But in practice, well, it ends up looking like alignment, but you should be careful not to conflate those 2, okay? Because attention serves other functions too. So the way that the attention model looks like is, on the encoder side, it's the exact same thing, okay? The encoder, all it does is it reads in a bunch of embeddings, and it produces a sequence of vectors, okay? So for each input, you have an output. No matter how many LSTMs you have, you eventually have some vector for every input. So now in your decoder, all you do is you have your attention model so that given the state of the decoder, you decide which part of the source you will attend over. And after you do that, well, I should have weighted my arcs to denote that this could be different, right? So let's say you pay attention to the very beginning, and then you sum them so that your context reflects the parts that you're actually paying attention, and now you have this context, and given that, you generate a new sentence, a new word. Now, the second time around, for the second word, you have a new decoder state, okay? And then given that, you pay attention, and you get a different span to look at, and now given that, you generate the output, and so forth. Okay? Just for the record, there's many different approaches. So the previous thing that I was talking about used RNNs to generate from left to right or to encode the sentence. You can do the exact same thing with convolutions, okay? Which have essentially are, if you think about our fixed length windows that you're looking at every step. And then all the rage these days are transformers. I don't know if you have heard of this, but transformers are really this idea taken to the extreme, right? So what we're saying is, with RNNs, we used to encode like either left to right or right to left. But how about for every word, we just look at all of the other words in the sentence, and that's called self-attention. And it's self-attention because for every word in the sentence, you look at the same sentence. Hence, it's self-attention, whereas attention, as it was originally introduced, it was between a target and the source sides, okay? So you have that, and then now you have a self-attention encoder, and the next part just looks the exact same way. So you have a self-attention encoder, you still have the attention between the decoder and the encoder, and now the only difference also is that this is also not an RNN, that's also a now left to right self-attention. So that your decoder, when you're generating this word, attends over the previous word that it has generated in the same manner that the encoder did. But it does not attend, if you think about it, into the future, because you have not generated yet these words, the future words. And if you look at how the attention weights look in the encoder, so essentially, what is the next representation for this particular position influenced by? Okay, so you have in the source you have a bunch of embeddings, but in the next layer where you have combined information from various words from the same sentence, then some of the attentions actually make a lot of sense linguistically. So maybe some of them detect long-term dependencies. Like in this example, you have attention for the verb making to the words more difficult, which is really a modifier if you think of the syntax of this sentence. So in order to actually inform the embedding for that particular position. So this model also has other nice properties, as in you can train it actually faster than RNNs because it's easily parallelizable in GPUs. And there are other parts that are also interesting, like you have shorter paths between all the output at the top to all of the source words, so that makes it easier to optimize and train. Although originally it was hard to train them, but these days you just download any toolkit and you can just use it almost out of the box. So as you want to spend like a few minutes to talk to you about the future directions or current directions that are still issues in neural NP. So I know it was like very fast, like this looking at how modern neural NP works, but really all it is you have a bunch of inputs and you learn a transformation into the output, okay? And that transformation is a bunch of multiplications in practice, okay? Along with a bunch of nonlinearities in between, okay? So that is not linguistically informed in any way, right? So in the symbolic systems, in the NP systems that we had, we were able to use a bit of linguistics, or of our not even linguistics, our knowledge about the language to define phrases to define alignments between phrases, or if we look back into the syntax, we were able to use syntax trees in order to describe patterns that we could apply, that we could use to do proper translation. Now, these neural models don't really do any of that. Well, maybe they do, but it's all done implicitly. Okay, so one very interesting direction is actually incorporating syntax and other linguistic intuitions into the neural model. And some of the people here at CMU have done some interesting work in this direction. Another interesting thing is how do you handle morphologically rich languages? So languages like Finnish or Turkish or any of the Native American like polysynthetic languages that cram a lot of meaning into single words as you think of them in English. Or another thing is how to actually train systems so that they are trained towards good translation quality. Because if you try to train an NLP system, you'll see that essentially what you're optimizing for is the log likelihood at every word, and that doesn't necessarily mean that if you have excellent predictions at every word, you will end up with a good sentence or a good translation sentence. Another interesting direction is training multilingual models, which is not something that we could have very easily done with symbolic phrase-based systems. So, for example, there's this very recent work from Google where they train systems on like 105 languages, so and translating between any of those. So let me just show you. Hopefully you'll show. They have a really cool blog post. So one issue with training neural nets is that you need a lot of data to make them work well. And you know, for English and French and German and Chinese, you might have so much data. But for languages like Swahili and translating from Swahili into Urdu, you don't have any parallel data. Okay, so how do you train a system to translate from Swahili to Urdu if you don't have any Swahili to Urdu data? So the idea here is that they trained a single system over 103 language pairs. So you have 103 languages and English. So you can train for translating from all of those into English or from English into all of those. Okay? If this line is the quality of the bilingual system for every language, then if you train a single multilingual system that has seen all of the languages, then it can essentially leverage similarities between related languages that happen to be very low resource, so that the quality of the single multilingual system is better for the really low resource languages. So you get really impressive improvements here, even though you get a slight or important degradation on the high resource language, okay, high resource ones. Although when they made that model a lot bigger to the point that only Google could train it and we couldn't, then you get improvements in all of the language pairs. So this is the original paper, and then they increased it to 6 billion parameters, and then they trained one with 50 billion parameters, and they got improvements in all of the language pairs. Yeah. So that's one very interesting direction, because again, one way to deal with the lack of data is to use data from related languages. Another thing here is, well, there was this paper that came up from Microsoft about 2 years ago that claimed that the machine translation models that they have, had achieved human parity. And they defined human parity as, you know, our model produces translations that are as good as our translators. And they got a lot of slack from the research community because that's really not true. Although, you know, they have really, really good systems. But then there was another paper later that pointed out that, you know, okay, we have learned to translate from sentence to sentence, but really there's phenomena that occur across sentences. So what we should be doing now is also to just translate at the document level. Okay. And there's many things that you couldn't properly translate unless you have proper context. And one of these examples has to do with, let me see if that's here. Okay, so that's the paper. So they evaluated.
You got 5 minutes.
Yeah. There's that, and then I'm done. Oops, I'm sorry. I thought I had it. Oh, no. Okay. So they compared the NP output and the. You can see it like that. So they gave human annotators the translation as it was produced by a human translator and the NP output, and they asked them to not give a score, but tell them which one of the two you think is better. Okay, and indeed, in some cases, the NP was better. So, indeed, in a significant portion, the human annotators selected the NP to be better in terms of adequacy. They were also almost better, in many cases, better in terms of fluency. But if you look at several discourse phenomena, that's in another paper. So yeah, there's a bunch of discourse phenomena that you cannot translate unless you have the proper context. So one example is, how do you translate some stuff like, does anyone speak Spanish? So how do you say, the doctor called me?
The doctor did what?
The doctor called me on the phone.
El doctor me llama.
So, el doctor me llamo, that means a male doctor called me.
Yeah.
Okay? So, if I told you to translate a female doctor called me, you'd say, la doctora me llamó, right? So, what if I told you a doctor called me, period, she said that I should take my medicine. Okay? Then, now, there's a clue in that second sentence, given from the context that, you should translate the doctor to la doctora rather than el doctor. Okay? Again, context, that's a very simple example of how context can help you to properly translate and not be influenced by biases that exist in the data. Because in that example, if you reverse it to the nurse called me, it's very common that the empty system that's just trained on a bunch of human-produced data, it will translate it to la enfermera. So the female nurse called me, although it could very well be a male nurse. Yeah, and I think the only other thing I have here is, as a future or very interesting research direction, is how do you handle domain adaptation and how do you handle different domains? So we have trained a model on a bunch of data that come from like news translations or translations of Harry Potter. Can we use that model to translate, biomedical data? And because of the different languages, like really different words have different distributions under different genres, right? Then being able to adapt between domains, just like humans do, is something that we cannot very easily do, exactly because we don't have a lot of data in all of those domains. Another thing is robustness to noise or to grammatical errors. So, for example, I'm not a native English speaker, so it's very possible, or if not 100% sure, that I actually made a ton of, or some grammatical mistakes while I was speaking to you, right? But you are all able to understand, hopefully, what I was saying, okay? However, in the current empty systems, because they have been trained on clean text as produced by professional translators, etc., then the slightest input that looks like noise, be that like a simple typo or an actual grammatical error that someone like me would make, then that would throw off the system because it's an input that it has not been trained to handle yet. So that's another thing, like training models to be robust to these types of noise or other types of noise also. And that's all I have. Yeah, if you are interested in NLP, Um, I mostly work with very low resource languages, like endangered languages. But there's a lot of people here at LGI that do machine translation work, so feel free to come by or yeah. So yeah, if you have any questions, I'd love to hear them more. Yeah.
When you're building a neural network that translates from one language to another, is it like when you want to go back from the target language to the source language, can you reuse parts of the neural network, or do you have to build a new model?
Very good question. By default, no. Although, because translation should be consistent, right? So if you think about it, if I go from English to French, and then I go back to English, I should get the same sentence, correct, that I started from. So there's some papers that utilize this idea, and there's many ways how you can do that. You can train like both directions at the same time, so that they agree with each other, or you can stack them on top of each other. So you get English as input, you produce French, and then you put it again through another system and you produce English, and you can propagate through the whole thing. Yeah, or you can do that, actually, that's one of the ideas that I haven't tested yet. You can do that across a third language, right? So if you have English, French, and German, if you go from English to German, and you go from English to French, and from French to German, these two translations should be the same, right? So yeah, there's some works on that try to enforce these ideas of like invertibility and transitivity. There's also some works where they try to tie the parameters, so like the French encoder in one side and the French decoder in the other direction, they might have similar or like some shared parameters. So yeah. Okay, well, I think that's all. If you have any questions later, I think we'll put up the slides in the video.